So hey look, my privacy matters.
Isn't it nice that Microsoft cares so much about you?
Oh yes. So database theory. Normalization part 1. So basically what we're talking about today, it's a bit of an oddball topic. It's it's a little bit of the Monty Python, and now for something completely different. Thus far, we have somewhat skirted the issue of actually designing databases. We have primarily been training you to be operators of databases rather than designers of tables. Today, we are going to be talking about table design. Normalization is the process by which you take data and you minimize the redundancy in that data. A certain amount of it is also getting away from the fact that there's not really a direct way to implement an array in these things, right? So, normalization. We want to develop a conceptual model that represents the entities of the enterprise and the relationships between them. This model is independent of any DBMS package, hardware, or the physical model. We are working in the realm of pure theory. Later, this would be mapped to an internal model that complies with the chosen database management system. Essentially, the question we are asking ourselves today, given a set of data, how do we break it into an ERD, entity relationship diagram? So, we use the normalization process to group data elements into tables representing entities. A lot of this is going to come down to, can you spot dependent fields which are dependent? Can you spot composite fields? A lot of this sort of hooks back into the nomenclature that we were discussing right friggin' at the beginning of this course, right? And it's been, enough time has elapsed since the test that I'm sure everybody's completely forgotten all of the definitions. That's why I'm here, to remind you, except if I've forgotten the definition, in which case I look it up. So, normalization is the process of organizing data to minimize redundancy. Normalized data doesn't have storage anomalies. We will discuss what we mean by the term storage anomalies. And the organizing of data is done by applying a series of rules to a data model. There is a formal process of normalization. Up to now, we have not been doing this in a sort of process-oriented way. We've simply been kind of squinting at a table and saying, yeah, that could probably be its own table, right? This is where we bring in the sort of formalized, rules-based, this is how it works, we'll do it this way kind of process. So, there are many normal forms. We will be discussing the first 3 of them. Once you've hit the 3rd normal form, you have removed the anomalies that we discussed earlier that I'm not actually going to show you until I've shown you how to do this. But we will be moving through the process of achieving first, second, and third normalization. We start off in zero normal form, which is unnormalized data, raw data at its most raw. We will not worry about voice, COD, fourth, fifth domain key normalization. Those are beyond the scope of what we're going to do here. And maybe they'll talk about it in advanced databases, I'm not sure. It's important to understand that this is a constructive process. Each normalization is built on the previous. It is not possible to proceed to second without having first done first. Make sense? So far so good? Good, good, good. All right. So, one of the purposes of normalization is to make databases efficient to maintain. It can, however, also make them more complex as data is now being separated into many different tables. This will require most entries, most queries, most select queries. Notice how select query is being used as a synonym for just plain query here, indicative of the attitudes of this course. This will require most queries to use table joins. So once your data has been normalized, you've got to be pretty comfortable using joins. But if you are comfortable using joins, then this is a much more efficient and effective way of doing things. So, let us consider the first normal form. Does this mark work? Good question. It does! Yay! I'm keeping it. So, the very first thing that we do to achieve first normal form is to remove repeating or multi-valued attributes to another entity. You cannot have multiple fields to capture multiple values. Let me show you some data. Ooh, that's very small. Okay, this is going to be our running example for a bit. So, what we have here is a table of purchase orders, right? We have order number, order date, customer ID, last name, first name, province, tax rate. Then we have product 1, product 2, product 3 with totals. You can see, probably, that this is an awful, awful, awful way to run a database. Can anybody tell me what an immediate and obvious problem with this is? Any speculation?
All the colored columns are basically like, essentially duplicates.
Well, they're not containing duplicate information, right?
Like they're basically the same category of thing.
They are the same category of thing. So, in the first order, we are ordering the cheese tray and the wine gift as two things. In 2, the bottle opener, the cheese tray, and the wine glass, right? So they are containing different data. What were you going to say?
Well, in the database that we're working on, we have like admissions and like the ICU and nurses and stuff. This is like someone took all of those and just dumped them into one table.
Very much so. This is, in fact, all of the data dumped into one table. So, consider this. This table has an implied maximum number of products which can be associated with an order. Right? If we want to add, if we want an order that has 4 products in it, we must modify the table schema in order to do so. this is deeply suboptimal, right?
Not ideal.
Certainly not ideal. So this is the purpose of the first normal form, is to eliminate this problem. Now, we can see that each of these fields is exactly and completely shared with each of these three headings. So, we can take them, take these products, take the product information, separate it out into a product table. We then refer to different products in this table using their product ID numbers. So, the most common problems with people, I'm not sure that it quite elevates itself to the level of sin. Certainly, order is better than chaos in database design, but, I'm not sure we need to get theological here. Anyway, most common problems that first normal form is attempting to fix are the lack of a primary key and the use of repeating columns. Another thing that we do in first normal form is remove calculated fields. In our database example, or in our data example here, I know it's very tiny, this final column is the total purchase amount of the order. This is a calculated value, and one of the things you do in first order normalization is to remove that data. It can be calculated from the other data, so you don't need to keep it, right? So, some of this kind of the design ethos that's going into this is a very it's a very 1970s, 80s kind of ethos. What we are attempting to minimize above all other concerns is the amount of space the database takes up. We are concerned with minimizing the memory footprint of the database. Yes?
What about province and tax rates?
I'm getting there.
Oh, okay, is that further in?
That's further in.
Yeah.
We still have 2 more normalization phases to go. So, first order normalization though, we're taking care of repeated columns and we're removing any calculated fields. So far so good? Okay. So, you may also say this table is currently wasting space due to the presence of these nulls, right? These nulls are physical space in the machine which is being wasted. So, in order to extract the products, right, we actually need to create 2 tables. So, let's consider the nature of the relationship between a product and an order. Can a product appear on multiple orders?
Yes.
Yes. Can an order contain multiple products?
Yes.
So what sort of relationship is this?
Many to many.
Many to many. So, once again, we do not have a direct way of creating a many-to-many relationship between 2 tables. We need to get there by means of a third. That is why, to represent the relationship between products and orders, we need 2 tables. Right? tables have been created, order and product. They are linked by the order field, order ID. This eliminates the repeating fields in a record, and the calculated fields, there are a couple other ones actually as well. X, price one, I don't know what X is standing for here.
I think that's like if there's like 10 items each for, there's 10 items each for 100, and then it's like, cost like 1,000.
Existing?
Yeah,
It's extended
Extended?
price, the sum of all the prices.
yeah,
So the
extended.
price times quantity.
Yeah.
Yes. Yeah, it's clearly price times quantity, yes. I didn't realize that the extended is the terminology for that. So this is also a calculated field and doesn't need to be kept. You can perform the multiplication on the fly and not keep the results of simple multiplication in your table. This also minimizes the amount of disk space the database is operating on. And you may say to yourself, okay, why are we so concerned about this? Memory is very cheap these days. This is certainly much more true in consumer electronics than it used to be. But keep in mind, when you are designing a database, a lot of the time that database is occurring on rented systems, right? When you put your database up on the cloud, you are paying for storage. If you minimize the amount of disk space that this database takes up, you are minimizing your cost to rent it somewhere. Yes?
Or if you just host it locally.
I mean, you're still having to pay for it. It depends on the size of the application,
Yeah.
right? Part of the part of the selling features of putting it up on the cloud are, if you run out of storage space for your database locally, that's a problem, and a problem that has to be solved by people going out and buying more machines, right? Whereas if it's on the cloud, you're simply just build more for usage.
So yeah, the cloud it's pretty much just for like bigger applications and not for like just keeping like a small database of a few items.
Yeah, it's the cloud people certainly would like you to think that the cloud should replace everything, but I certainly believe that there's a strong reason to maintain local data storage. For one thing, if it's in-house, you don't have to worry about, the cloud service being hacked, right? You have to worry about yourself being hacked.
Yeah, it's kind of like in the same realm of like the preservation of physical media, compared to like digital media. It's not exactly the same, but it's similar.
Yeah. There's also the issue of did you fully read the terms of service of the cloud service that you're using? Are they using your data? Are they training AI models on your data? These are entirely probable and possible things. Maybe for reasons of information privacy and security, you want to keep it off the cloud.
Yeah.
But that being said, if you are one way or the other, you're either paying for storage in large increments as you buy hard drives, or small increments as you increase the amount you're renting from a cloud service. So it's certainly cheaper than it used to be, but it's still worth minimizing the size of your database, particularly as it grows. Yes. Good. So, first, normal form. We have taken our orders. Ooh, I misspoke. Right now we have split the table into two tables. We're going to be setting up the many-to-many relationship a little bit down the line. So we've split our table into two smaller tables. See, that's one of the conceptual hurdles of normal forms is you want to kind of jump ahead in them and not walk through them methodically. So we've taken our order and our product, and we are saying, order 239 has two entries in the products table, cheese tray and wine gift. right? Here are the product numbers. So you can see we have repetition of the order number within the products table. There's some redundancy here that will be minimized in a future step, but at the moment, this is our first normal form. A great degree of redundancy has been removed. And certainly, it's no longer the case that the number of products associated with a particular order is limited to 3. We can have as many entries in this table as we wish, and they don't even necessarily have to be in any particular order. Does that make sense? Very good. So, any questions? If you'll forgive me for just a moment, I'd like to skip ahead because there's something that's important and relevant, but it's in the wrong place in the slides. So this is another way of representing what we represented previously with repeated product columns. Sometimes you'll see, oh, well, this order, here's the order number, blank, blank. You know, in an Excel spreadsheet, blank, blank like this means repeat, like it's ditto, right? Repeat the above, repeat the above. And then we have, 3 items associated with this order represented in this way. If we represent this in first normal form, these null rows are eliminated, right? These rows which sort of are supposed to have this data copied, right? Those are now gone from our first normal form. That's the other way that you could organize this, right? Make sense?
Because they're empty?
Well, because they don't contain any unique data, right? In this particular example, if you filled in these blanks so that these were complete records, for every time you wanted to list a different product in an order, you would have to relist what the order number is, what date it was made on, what the vendor is, what their address is. All of that data would have to occur in the database 2 more times, once for every product in the order, right? Which is obviously wrong and bad, right? So when we go to first normal form, there we go. You'll notice there is no redundancy in the orders table with respect to order IDs, right? We have no extra lines here. Now, we do have some redundancy, but not with respect to orders. What kind of redundancy do we have in this table right now? In this table, what kind of redundancy do we have right now?
Maybe that the last name and first name could just be one field.
Not necessarily. I think it's fine to keep those as, we don't necessarily, we're not necessarily reducing the amount of storage we need by taking 2 and making them a compound entity. Sorry? Customer ID, that's right. Notice that customer ID is now containing repetition, right? So that might be one of our future targets. What about repetition inside of the product table? What repetition do we see? Repetition here.
Product description needs a product that can be separated.
Product ID.
Yes. So in this table, every time a product is associated with an order, that product gets all of its information repeated. Now, you can imagine that this is probably a pain for one thing, there are no products which can exist independent of an order. A product does not exist until there's an order for it. That's probably not optimal, right? For one thing, how do you put a product in your product catalog when nobody's ordered it before if you require an order to put it in the product catalog? Right? It's like a chicken and egg problem. What you do is you get one of your employees to buy one, and then then they have a purchase in the database, right? But it's $10,000. It's like, we just gave you a one-time bonus of $10,000.
I feel like a lot of companies would just make the employee pay out of pocket as part of their job requirements.
That too. But you can see where the redundancy is still residing here, right? Our next objective, second normal form. Hate it. I'm like gonna get carpal tunnel by the end of this bloody semester from the forward arrow, from all the videos I have to watch. It's like, get to the point, get to the point. Second normal form. We create another table, order line. It is linked to the product table with the common field product. Therefore, each product description is entered once in the database, rather than each time someone purchases the item. Yes?
Why isn't it linked to the product table using a join table sort of thing?
So the join operation is what we use during a select query to view the data. What we're talking about here is the organization of the tables themselves. Unless we organize the tables this way, there's nothing to join over. Does that make sense?
Can you say that last part again?
So unless we sort out taking products, putting the products in their own table, taking orders, putting the orders in their own table, taking customers, putting them in their own table,
Yeah.
we have nothing to join over,
Oh.
right? So joining is not a replacement for create table with a schema. Make sense?
Yeah.
Yeah. You're welcome. So, yeah. Another problem with this, because the product description is every single time you enter something here, you have to repeat the description, which means presumably you have to look it up from somewhere. And also, if you ever needed to edit what the price was of an item, you must edit it everywhere in the table, but that also means you're going back into historical orders and modifying how much people paid for things in the past, right? That's actually an issue that's not addressed by the time we're finished all of this, but that's okay. So, the primary key for each record must be able to determine the value for all of the other fields in the record. That's the big issue. So, basically, in this case, we're doing okay, right? All of our primary keys in the order table correspond to actually different transactions. However, here, we have neither of these is a primary key, right? So, here, knowledge of product number alone provides the product description and price without the order number. So, if you consider this in terms of field dependency, product description, product description and price are entirely dependent on product, right? Quantity is dependent, Well, it's not dependent on order either, right? That's separate. The quantity is not dependent on the product ID, right? Because here we have we're ordering 10 555s, here we're ordering 20 555s. So quantity is not dependent on product ID, but price and product description are. So those we can take out, make it into its own table, right? Another table has been created, order line. It is linked to the product table with the common field product. I read that already. Did I? Therefore, each product description is entered once into the database rather than each time someone enters or purchases a product. A combination of order number and product number are needed to identify quantity. There we go. We've taken those two tables and clicked them apart. We now have a product table where every product ID occurs only once. This is now a primary key. It's now unique. Our order lines are an association between two foreign keys and a description of the quantity of that item that's been added to that order. Right? Is this making sense? Any questions? All right. Is there any redundancy in this table?
Yeah, the first, organize at the same time to repeat.
Mm-hmm. We do have repetition here, and we do have repetition here. Can this repetition be eliminated?
Maybe make more tables?
You have to create.
So this repetition cannot be eliminated, right? This is that sandwiching table, right? This is the thing that does many to many, right? We can't, there's no further that this can be simplified. How about this one? Can this be simplified any further? Also no. Every description has precisely one that it corresponds to. There's no redundancy with respect to products. There may be some redundancy with respect to price, but it is not an error that two items in a product database should have the same cost. Question?
What was the difference in like the separating of tables that we did in the first normal form versus this one?
Good question. So in the case of the first normal form, we had redundant sets of attributes, right? These were crunched into one and extracted into their own table, right? If you'll notice, when we did that, we had to keep the order ID column in both, right? But all of those in like, product 1, product 2 associated with every order, all of these were dumped into this table. Right? Make sense?
So the first one was like removing duplicate columns, and then
Yes.
the second one was removing as many duplicate like actual values as we could.
Yes. Yeah. So the first is an attack on columns. The second is an attack on rows. Yeah.
Or records.
Yes. Rows or records, columns or attributes. So the order table that started with 23 fields has now shrunk considerably. Third normal form will reduce this further by removing the redundant names, provinces, and tax rates. So, to review, the purpose of second normal form is to eliminate redundancy in the rows. We are now going to examine in third normal form redundancy with respect to dependent attributes. Consider tax rate. Tax rate is set by a province, so the tax rate is entirely dependent on the province, right? It is still important to keep the tax rate in the table, right? But, pardon me, this column is entirely dependent on that column, right? We might even say that last name and first name are entirely dependent on a customer ID as well.
And province.
I think so, yeah. Yeah, I'm willing to say that.
Customers down to province.
So, the third normal form is violated when a non-key field is a fact about another non-key field. So that's what makes this the third normal form. In second, we were applying all of this to IDs. Here, these are not primary keys, right? This is probably going to be a primary key, but it's not a primary key in this table, right? It's not this table's primary key. This is like, if you look at this, you should say, this is obviously a foreign key. It's just, to a table that's not exterior yet. So, reduce second normal form entities to third normal form by removing attributes that are dependent on other attributes. So, for example, by creating another two tables, our order table is shaved down to 3 columns. We now only have order, order date, and customer ID. We've eliminated the name fields by linking customer ID to a separate customer table, and likewise for tax rate using the province abbreviation. So you can see that because province does not occur in this table, it's occurring in the customers table. This removes the redundancy of the customer name and province each time an order is placed. So you can see our customers are given as such, right? We no longer have any redundancy with respect to customers. Further, the tax rate is removed by creating a table with province tax information, which, if you think about it, is probably exactly the sort of table you would expect to exist, right? That makes a certain degree of intuitive sense that you would have a table whose only purpose was to look up the tax rate for a particular province or jurisdiction. Make sense? So far, so good? The original unnormalized order table has become 5 normalized tables. Customers, orders, order lines, products, and provinces. These are the fields contained in each of these tables, but this should look extremely ugly to you, just very, very ugly. You should think to yourself, that should be a diagram. and so it shall. Orders, order lines, products, customers, and provinces. Notice that each of these has a primary key. Notice that in the case of provinces, the province code itself is the primary key, despite the fact that it's not a number, right? Perhaps we could have, province numbers, but, the example is already complicated enough, I guess. So, so we have all of these boxes with all of our values indicated. The next thing that we need to do, identify where the foreign keys lie. Customer ID is a foreign key. Both of these are actually foreign keys. Province ID is a foreign key. Once we know where the primary keys and where the foreign keys are, we can draw the arrows. Each foreign key means that there is a relationship between two tables. The primary key is the one side, and the foreign key is the many side. So you can see we have a foreign key for customers, so we have a many side here, a one side there for customers, right? A customer may have many orders, but an order may only have one customer. Customers have a foreign key of province. A province may have many customers which reside in it, but a customer only resides in one province. Order lines is the implementation of the many-to-many, right? An order can be associated with many products, but a product may be associated with many orders. This is organized by means of this middle table. Make sense? Questions? Very good. So, this increases processing complexity. In order to get useful information out of the database, most queries will need to join two or more tables, but this means that the data is organized and unique. Each fact is stored in only one place. Now, again, the effort has been to minimize the memory footprint of the database. This has come at the cost of processing time, right? All of you, over time, should become very familiar with this trade-off. This trade-off occurs again and again and again in our field. You are spending some memory to get some processing time, or reducing memory, but increasing processing time, right? It's all about the trade-off. However, when it comes to this, you might not be getting as much out of the processing side as you may think. You may think, oh, well, I don't have to do joins. That increases my processing speed, so maybe I should just leave everything in one gigantic table. Well, in order to perform the data maintenance that's necessary to keep that table in shape, you're going to have to add procedures, and you're going to have to add triggers, and a lot of them. And it's not going to be fun, because triggers and procedures are programmed in the worst programming language that exists, TSQL. So, normalizing is a good thing. Don't leave your data unnormalized because it makes it problematic. So, quick summary. First, normal form. Make a separate table for each set of related attributes and give each table a primary key. Eliminate redundant columns. Second normal form. Eliminate redundant data. If an attribute depends on only part of a composite key, remove it to a separate table. Attack the rows according to primary keys. Third normal form. Eliminate columns not dependent on a key. If attributes do not contribute to a description of a key, remove them to a separate table. Attack data redundancy according to not the primary keys, but everything else. Make sense? Questions? All right. More examples. Who cares? Case study. I'm gonna skip through to a bit that I consider more interesting. I think these slides are slightly out of order. So, I'd like to now discuss storage anomalies as they pertain to the first, second, and third normal forms. So, all of this is also true of zeroth, the unnormalized data. So, first normal form is subject to insertion, update, and delete anomalies. So, for insertion anomaly, recall the first normal form again for this purchase order. If the database had only this table in it, we could not set up a vendor or item unless we had a product order information. So this is what we mean by insertion anomaly. It is not possible to insert vendors just by themselves. And this is a thing that you probably want to be able to do. It's also not possible to insert a product that does without having an order for it. This is the insertion anomaly is what I was referring to earlier. Make sense? It's still possible to do it, of course, like you can do it with triggers and procedures, but maybe you should reconsider your table organization first. Update anomaly. If the description for an item changes, we would have to find the description and change all occurrences. This is, again, increasing the complexity of update operations. Not impossible, but not optimal. And the deletion anomaly. Deleting the row for a purchase order may cause the loss of vendor and item information. If you delete an order, unless there's another copy of the vendor and the product in the database, the information can just be lost. Again, you can prevent this data loss by preventing the deletion using stored procedures and triggers, or perhaps just very intelligent select statements, but we could be using much simpler queries if we design our database properly. And simple queries also take less time to process, in some cases. Make sense? Any questions? Very good. Storage anomalies of the second normal form. It's a very formal sounding title. So, under the second normal form, under insertion, items can be added by themselves without product information, or without purchase order information. So, we can add a product just by itself, we can add a vendor just by itself. For updates, if the description for an item changes, only one occurrence would be affected. And deleting a row for a purchase order has no effect on the item record. So we have solved the anomalies of the first normal form. However, we introduce some new anomalies. A vendor cannot be set up by itself. Let's take a look at that for a moment. So notice that this is the first normal form, right? So our products over here are going to be extracted. Notice the repetition in the primary key, right? So all three of these are on the same order, right? So this is the redundancy that we would be eliminating at the next step, right? But once we've done that, we're still in the position where we could have multiple vendors associated with one product order. Or, sorry, scratch that, reverse it. We could have multiple product orders associated with one vendor, right? So we've not yet eliminated, we've not yet cured the problem of vendors being inserted in and of themselves. Under update, multiple records may be needed to be updated if vendor address or information changes. And under deletion, deleting a row for a product order causes loss of vendor information. So basically, we have all the same problems that we had for products, but we now have them for vendors. And we also had them for vendors before, but in one of the second normal form relations, we have a transitive dependency between one non-key attribute, vend ID, and other non-key attributes, name, address, city, province, and postal code. The transitivity is removed when vendor has its own relation in the database. So once we have achieved then the third normal form, vendors can be set up by themselves, so we've solved the insertion problem. Only one record needs updating if information about a vendor changes. We've solved the update problem. Deleting rows for a product order does not cause data loss for vendors. So the deletion problem has been solved. So we are good. We have eliminated all of our anomalies by achieving the third normal form. At least the ones that we're currently talking about. Make sense? How many people are looking at their phones?
Not me.
So let's go back a bit. Let's do a bit of a case study. We have Pipes and Things Incorporated, distributor of plumbing parts and fixtures. They purchase things from manufacturers and supply retailers, so they're kind of like a middleware, you know. They're mid-level retailers, these guys. We are designing a database. Our first object is to determine what the entities even are in the first place. So, let's take a look at their purchase orders, right? This is what a purchase order, like, you know, how many people have ever seen a purchase order? Good, a few of you. This is probably a simplified version of the sorts of things that you see. So important information is located here. What the order number is, what vendor is making the order, the date that the order was made, the information respecting the vendor themselves, the items, quantities, IDs, descriptions, prices, and totals, and the grand total at the end. All of this information is present in the purchase order. Under zeroth normal form, we take this information and dump it directly into a table. Here's another one. Take those two, dump them into a table, and this is what we get. Right? So, we have multiple occurrences of the data, we have multiple redundancies. Notice that delta cartridges occurs both on these two purchase orders. We can find in cells that have more than one value. We can find cells that have more than one value. Yes. So, again, the implication here is that anywhere you have a blank spot, it means repeat from line above, right? So, if we were to go about producing first normal form of this data, how would we do that?
Get rid of the total column.
Yes. Very first thing, total column is scrapped. Just like that. Anything else we can scrap? Any calculated columns that we can scrap here?
The line total.
Line total is also calculated. It's calculated from price and quantity.
That's enough.
Yeah. So, all right. Do we have any more calculated values? How many people think yes? And how many people think no? I'd say the no's have it. So, the next piece of redundancy that we have to address, what is it? Under first normal form. This is slightly reviewed from earlier in the lesson.
So if there's a repetition of similar columns.
Right. In the first table, because of the way the first table was organized, we had like product 1, product 2, product 3. Here, it's been stacked vertically, but it's still intending the same thing, right? So really, the redundancy we're looking to eliminate is this. We're trying to get rid of these things, which are not considered even important enough in this table to even be worth putting data in for in an Excel spreadsheet. So we're trying to eliminate these, right? Make sense? So, we take this and we split it. We end up with this being order, this being order, I guess it would be product at this point. Product. Product also requires a copy of the purchase order ID. Make sense? So far so good? We end up with an order table with only 2 lines, right? Same mistake on both sides, oh my goodness. Throw it out. And you need this column over in here as well, right? First normal form. So far so good? We get 2 tables, one with 2 entries, one with 5. Now, yes. So next, oh man, as soon as I change slides, all my hard work goes away. Huh? I may just leave that up though. I have to erase it. So, next, what we're trying to do, we need to find out which items are dependent on the key, and what items are dependent on the what data items are left dependent on the whole key. Wait, on parts of the whole key. What data items are dependent on parts of the key? What data items are left dependent on the whole key? Oh, right, because they've said that the table's key is the combination of product order and item ID, right? Because like neither one of those is a primary key in this table because both have repetition, right? So the real primary key is like a composite of those two, at least until we eliminate it. So items which are dependent on the product, or the purchase order, this one, 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 right? And yes, product, things which are dependent on the item ID are description and price, right? So, our resulting table, after a second normal form, we have a product order number, the date, the vending, the item vended, name, address, city, province, postal code. The ID is, the item ID is the primary key. We then get description and price. The attributes remaining as dependent on the original key are quantity. So of these two, like of all of this data, quantity is the only column that is independent of both item ID and purchase order ID, right? It has variations with, it's not held constant as either of these columns are held constant, right? That's another way to think about dependency. It needs to be held constant when the other is held constant. It doesn't do that for either of these, so it's dependent on both. So we need to make another table for quantity, introducing the order number and the ID number. Separating any entity that deserves its own relation into the database. This is part of the third step. We then name each entity, look for a field that has a dependent attribute, a key for another entity, ask us ourselves if this is already occurring in the second normal form table, and if so, where? We then end up with product order headers, gives you date and the vendor ID, as well as the order number. Vendors give you the vendor ID, name, address, city, and postal code, and province. Items give you item ID, description, and price. And lines gives you an association between product orders, item IDs, and quantities. Very similar to the previous example, actually. If we collect all of those into boxes and label the primary keys, we have the beginnings of an entity relationship diagram. So, this half of the room. Where are the foreign keys?
And
Any others?
PO no and item ID.
Any others?
Could province be a foreign key?
Well, it was in the last one, but that's because we had a table indicating tax rates. We don't have that in this one, so no. Well, remember that every time we have a foreign key, that establishes one line, right? So, 3 tables can be interrelated by, or 4 tables can be interrelated by 3 lines. Let's see what it looks like. So, the side with the primary key is the one side. The side with the foreign key is the many side. So, there you go. Foreign key, primary key, foreign key, primary key. There we go. I'll pencil that in for you. Yeah. You guys over here. Foreign key to primary, this one, foreign key to primary key. Foreign key to primary key. And foreign key to primary key. Let's see how we did. Whoa. Yay! Although it's unfortunately the diagram has moved, but yes, we did it right. Very good. Yay! Whoa. Summary. Normalized data does not have storage anomalies. First normal form eliminates repeating groups and derived attributes. Second, eliminates redundant data. Third, eliminates columns not dependent on the key. Any questions? In that case, thank you and good evening.